Okay, so this section is all about using different machines and like what are machines and what's the advantage of using a machine. So if we go to the second slide, what is a machine? So a machine is a device that makes doing work easier. If you think about things that you have used that make work easier, can you think of any things that would be considered machines that you have used today? So maybe some things that you might think of are like a stapler. So if you are trying to bind two pieces of paper together, a stapler makes that easier. Maybe another machine would be like a scissors. If you are trying to cut something, using a scissors is easier than trying to use something else. Other things that would be maybe considered a machine, something like a bicycle. If you ride a bike, okay, it makes getting to different places easier or moving around easier. But the purpose of a machine is to make some type of work easier. And if it's not making work easier, then the machine is not really worth using. Okay, so let's see. So machines increase the force applied. So machines can do different things in order to make work easier, but one way they do that is they can increase the amount of force that a person is applying. So for instance, like a bottle opener, if you've ever tried to open a bottle that is not like a twist off cap without a bottle opener, it's very, very difficult, nearly impossible to do that because you can't apply the amount of force that's needed. A bottle opener increases that amount of force that you apply and causes the cap to actually bend and then open, come off the bottle. If you've ever used a car jack before or ever seen someone use a car jack, the purpose is to get the car off the ground. It increases the amount of force that you can apply to the car. So you could try to lift up the car, but it's going to require quite a bit of force. And if you use that car jack, it's going to apply a greater amount of force so that the car actually gets off the ground. Remember that work equals force times distance. So for some objects, okay, the way that they do this to increase the amount of force that you can apply is the same amount of work can be done by either applying a small force over a long distance or a large force over a short distance. So sort of what that looks like is if you were to do the equation two different ways. So I could either do let me get my little writing utensil. W equals small force over big distance. You can have the same amount of W if you use big force over small distance, small d. Sorry, that's supposed to be a small d. Okay, so what the machine does to increase the force is you apply a small amount of force over a long distance, and then that machine changes it and uses a short distance and can apply a larger force over that. Can you think of any other machines that might multiply or increase the amount of force that you can use? So be thinking of that. Okay, another way that machines can change the force is they can increase the distance that the force is applied. When they do that, therefore, the force that you feel you have to apply seems less than what it would be over a short amount of distance. So for instance, a ramp is a type of machine. It makes doing work easier. So if you look at this picture, the two guys are trying to get that box or whatever it is up into the truck. If they didn't have the ramp, they could just lift it, but with that short amount of distance, you'd have to apply a lot of force in order to get it to lift up. And so the ramp increases the amount of distance that you apply the force, which therefore is going to decrease the amount of force that you have to do. So it's the same amount of force or same amount of work to do it, either to lift the object or to push it up the ramp. But because you increase the distance, that means the force is going to go down. So it's the same amount, same thing as like we talked about on the other side. If we have the work and we make a big force over a small amount of distance, which would be just straight lifting it up into the truck, we could also get that same amount of work by doing a small force over a bigger distance, which is like using the ramp. That's what they're doing right there. Okay. Another way that machines can make work easier, so besides increasing the amount of force or changing the distance that the force is applied, they can also change the direction of the force. So think about like window blinds. What we want the window blinds to do is to go up, but we don't have to push them up. Typically, for a lot of window blinds, you'll see the little pull chains, and you pull down and the chain and the windows go up. And so it's changing the direction of the force. It's easier to pull something down than it is to push it straight up. A car jack does the same thing. So if you have ever used a car jack, what you do is you push down on that part, and then the car jack pushes the car up. So rather than pushing up on the car and trying to push it up yourself, you push down, which is an easier direction to push, and the car jack pushes it up. If you've ever chopped wood before, seen someone chop wood, so you apply a force downward on the axe, and then the axe is going to split the wood, and it's going to make the force change into like this horizontal direction, making the wood go apart from one another. So think about other machines that might change the direction that you have to apply the force. Okay, so when we're talking about machines, we talk about several different forces. There's an effort force and there's a resistance force. The effort force is going to be symbolized with this capital F, and then you can see the subscript E. That E is for effort. So in these equations that we use for machines, because there's two different forces, so the force that you apply, that's the effort force, and then we have the resistance force, which is the force applied by the machine to overcome resistance. The resistance force is going to be F and then a subscript R. And if we look over here at this example of pulling a nail out of a hammer, okay, this would be like the effort force right here. You are applying the effort force, and then this right here, whatever the hammer is applying to the nail, that's the resistance force. The other two things on this slide are we've got input work and output work. So the input work is the work done by the person on the machine. That is done by the effort force. So the effort force and the input work are going to be related to one another. We're going to symbolize that as a capital W and then IN as the subscript. So that means work that you put into it. The output work is what is the work done by the machine. So that'll be capital W and then out as a subscript to show that's the work we get out. And so the resistance force and the work output are going to be related to one another, whereas the effort force and the input work were related to one another. Okay, so when we use machines, okay, we do not transfer all of the energy to the object. So what happens is when I do work to the hammer, so like when I am pulling on the hammer, I transfer energy to the hammer. So energy from my hand goes into the hammer, the handle. The hammer is doing work on the nail by like pulling it out of the wood. So the hammer is transferring energy to the nail. But the problem is that when we do this, some of the energy is transferred or transformed into thermal energy because of friction. So think about when the hammer is pulling that nail out of the piece of wood. If you've ever done this before, it actually gets really, really hot. Like if you pull the nail out and then touch the nail, it's really hot because there's a lot of friction there. And so some of the energy that that the hammer was applying to the nail is actually changing into thermal energy rather than going all into like kinetic energy by moving the nail out. And so because of that, we have this really important thing that the work output is always smaller than the work that you put into it. So I could put 10 joules of work into it, but only get 9 joules of work out because one of the joules was changed into thermal energy because of friction. So please make a note of that the work out is always smaller than the work in. Okay, now ideally, that wouldn't happen. Ideally, in an ideal world, we wouldn't be losing energy to friction. And so in something called an ideal machine, this work out that you're getting, so the work that we get out of the machine is actually equal to the work in because we're not losing any friction energy. We're not losing any energy to friction. So we're going to do a practice problem using that concept that the work out is equal to the work in. You can only do this for ideal machines, okay? So this is not like in our real world, but we can use the work out equals work in order to solve this practice problem. So let's suppose that the hammer claw moves the nail 0.10 meters. If the resistance force is 1,500 newtons and you move the hammer handle 0.5 meters, what is the effort force that you must apply? So if we look at the equation, the work out equals work in. If you remember, work is equal to force times distance. So the work out is going to be force times distance. The work in is force times distance. Now, remember from a couple slides ago, we were talking about we have force, the effort force and the resistance force. And so the effort force is related to the work in. And so I'm going to specifically put an E there to remind myself that that's the effort force, the work that I was putting in. And then the work out is related to the resistance force. So you put a little R there to remind yourself that that is the resistance force. And then we will relate the distances to those two things. So if we plug things into this equation, suppose that the hammer claw moves the nail 0.1 meters. If the resistance force is 1,500 newtons, and you move the hammer handle 0.5 meters, what is the effort force? So we're looking for the FE. That means that we must know the FR. So the resistance force, they tell us, is 1,500 newtons. The distance that the resistance force is moving, okay? If we look at this, we have the hammer claws moving the nail 0.1 meters, and you move the hammer handle 0.5. The 0.1 meters, the 0.10, that's going to be our distance that the resistance moves because that's what the hammer is moving the nail. And then, let's see, so then we're looking for the effort force, and the distance that you are moving the hammer handle is 0.5 meters. So if we're trying to solve this equation, I would first go ahead and multiply that left-hand side, so 1,500 times 0.1. So we've got 150. That is equal to the effort force, which is what we're trying to find. And the effort force is multiplied by 0.5. Okay, and then the next algebra step is divide by the 0.5. So that goes away. And the effort force we're left with, 150 divided by 0.5 is 300. Remember that anytime you have a force, it's measured in newtons. And so the effort force was 300 newtons, which is really cool because if you look at it, the effort force that you had to put into it was only 300 newtons, but you got a resistance force or an output force of 1,500 newtons. And so we're really multiplying the amount of force that was applied by using the hammer rather than just using your hands. All right. So we have this thing called mechanical advantage. The symbol of it is just capital M, capital A. This is how much the machine multiplies the effort force. And so ideally, we want the mechanical advantage to be large, because that means that the machine is multiplying the effort force by quite a bit. To find the mechanical advantage, you would do the resistance force divided by the effort force. Now, when only the direction of the force is changing, so like the effort force and the resistance force are equal, but we're just changing the direction of the force to make it a little easier, so we're pulling down rather than pulling up, the mechanical advantage is obviously going to be 1 because the effort and the resistance were equal to one another. So if we solve a mechanical advantage problem, we're calculating the mechanical advantage of a crowbar. If you're not sure what a crowbar is, you might want to look that up. It's also used to like get nails out of things. It's sort of like the back of a hammer, kind of looks like that. To which you apply 100 newtons of force to lift 250 Newton rock. Okay, it also lifts things. So we're going to do mechanical advantage equals, and it's going to be the resistance force over the effort force. So you are applying 100 newtons. That means that's the effort force, because you apply it. And so the resistance force must be 250, and we're going to divide that by 100. So 250 divided by 100 is 2.5. Because it is force divided by force, or newtons divided by newtons, there's actually no unit for mechanical advantage. It's just a number. But what this tells us is that this crowbar is multiplying the force that we can apply by 2.5 times, or 2.5 times more force than we could have with just our hands. Okay, so efficiency. This is measuring basically how is the output work related to the input work. Now, obviously, in an ideal machine, the output work and the input work are the same, and so the efficiency is like 100%. We would like for that to happen. Now, in a real machine, so one where there is friction and we're losing some energy to thermal energy because of that friction, then the efficiency is going to be less than 100% because the output work is not going to be quite as much as the input work. But this efficiency number is going to give us like a percent of how well the machine is working, or how much of it is actually going into work and how much is being lost to friction. So ideally we want a high efficiency. The way that you can make a machine more efficient would be to somehow reduce friction. And so think of a way that you could reduce friction when using that type of machine. So the equation is efficiency equals work out divided by work in times 100%. And it's going to give you an answer as a percentage. We're going to do an example with efficiency on this next slide. So we're using a ramp 7 meters long. Joe applies an effort force of 989 newtons to move a 1500 Newton box onto a truck 1.5 meters high. What is the efficiency of the ramp? Okay, so efficiency, if you remember from the last slide, I'm just going to actually abbreviate as E. Okay, so E equals the work out over work in times 100. Okay, so we need to solve for work out, we need to solve for work in, and then we're going to divide and then multiply by 100. So the work out, if you recall, work is equal to force times distance, and the work out, if you remember the input force, effort force, resistance force, the work out is related to the resistance force. So we're going to do resistance force times the distance for work out, and then work in would be the effort force times the distance that we move it. Okay, so if we go look at work out first, so we're using a ramp that is 7 meters long. Joe applies an effort force of 989 newtons to move a 1500 Newton box. It may actually be easier to pick out which one is the effort force. So Joe applies an effort force of 989 newtons. Okay, so we know that this effort force is 989. And then we just need to know, like, what is the distance that effort force is applied. And so he is actually moving this or applying this force over 7 meters because he's applying it all the way up the ramp. Okay, the output, the resistance force is going to be the box, which is the 1500 newtons. So it's the other force that's left. And the distance that the box is moving it is moving from the ground up onto the truck, which is that 1.5 meters high. The efficiency equation, probably the most difficult part about it is figuring out what's the resistance force and what distance goes with that, what's the effort force and what distance goes with that. Okay, so once you have those, then you're just kind of plugging it in. So the output work, the work coming out is 1500 times 1.5, which is 2,250 joules. Okay, the input work then is 989 times 7, so 6,923 joules. Okay, so then we need to plug it into our efficiency equation. So efficiency equals work out on top, so 2,250 on top, the work in on the bottom, 6,923 on the bottom, and then we're going to multiply that number by 100. So 2,250 divided by 6,923, it gives me 0.325, and we're multiplying that by 100, and it'll give me 32.50%. So that at the end, your efficiency is going to be a type of percent. This efficiency is not actually that great. If we get close to 100, then that means it's a really efficient machine. Our ramp is not actually very efficient. We're losing a lot of this work or a lot of energy to friction in this case. And so this ramp is actually not quite that efficient. Hopefully this makes sense. I'm going to post this video on Blackboard as well. So if you need to go back and rewatch it and stop it or pause it and then look through your notes and make sure you understand how to do this, make sure you know how to do all of these calculations and you know all of these definitions from this video.